So it is my pleasure to present Professor John Kececioglu. John is a professor of computer science at the Bio5 Institute of the University of Arizona, working in the design, analysis, implementation, and evaluation of discrete algorithms for bioinformatics and computational biology. He did his PhD with Gene Myers and his postdoctoral study with David Sankoff and Dan Gusfield. His research has made fundamental contributions to algorithms for genome sequence assembly, genome rearrangements, multiple sequence alignment, inverse alignment, and parameter advising, with a book on parameter advising for multiple sequence alignment published by Springer. His recent work has focused on algorithms and software tools for pathway inference in metabolic networks. Thank you so much, John, for accepting our invitation, and the floor is yours.
Thanks so much, Susanna. It's a real pleasure to be here. Can everyone hear me and see the first slide of my talk? All right, yes. Great. So, yes, I'm really pleased to be able to talk here. I'm going to speak about some recent work that we've done on inferring pathways and metabolic networks via two different computational models, factories and hyperpaths. And we're going to discuss algorithms that are actually able to compute optimal solutions to these problems. And then we're also going to evaluate them computationally on actual data. So this is joint work with Spencer Krieger. Spencer is a former PhD student of mine. He's now a postdoc at Carnegie Mellon University. He's the Lane Fellow in computational biology, working with John Ma. And he's also going to be going on the job market, looking for a faculty position soon. This work that I'll talk about was published at Recom 2023, the work on hyperpaths, and then this year's Recom 2024, the work on factories. And journal versions have appeared in the Journal of Computational Biology last year, 2023, and then the work on hyperpaths was just published in a journal paper appearing at the special issue of Journal of Computational Biology last month. So fairly recent work. All right, so to give some background on pathways, as we know, pathway, it's a collection of reactions culminating in a specific cellular response. There's many different pathways that this community knows about, and here's a standard one with glucose and insulin uptake. Metabolic networks contain reactions from many annotated pathways, and we have many well-known metabolic networks worked out by the biological community. And we have excellent databases of these networks that contain metabolic networks from many different organisms. So we have a lot of data that we can actually compute on. So we're going to look here at pathway inference. I would say that in general, the task is given a set of available source compounds and a set of target molecules, find a collection of reactions that produce the targets from the sources. So the sources are, initial compounds from which the reactions can proceed, and the targets are molecules that we want to be producing from this set of reactions. And in general, we can have, a set of sources. These are really candidates. We don't have to necessarily use all the sources, but we do want to produce all the targets. So in general, we can have not just a single target, but a set of targets. Pathway inference, identifying reactions that do this has many different purposes. They can identify crosstalk between different pathways. So I have a pathway 1 and a pathway 2. I can identify that there's actually interactions between these two pathways. And as well, if there's some disease symptom of interest that's modeled by a particular target molecule being produced, we can infer a pathway and then infer, candidate targets that we might address therapeutically by designing drugs. So there are many possible uses of pathway inference. So we're going to be looking at reactions. In general, there's an entire set of reactants that are the inputs to this given reaction, and an entire set of products that are produced by the reaction once it completes. We have stoichiometries that are giving the relative ratios on the amounts of reactants consumed and reactants produced. And in general, a reaction consumes all of its reactants and produces all of its products. So we're going to be working with graph models and to infer these pathways. And in the graphs, we're going to be representing these reactions as edges. So traditionally, there are many algorithms developed where these reactions are actually represented using ordinary graphs. In fact, the majority of the literature from the computer science standpoint does this. And this really loses a lot of information because, as we said, it's all of the reactants that must be present and are used and produce all of the set of reactants. So if we model a compound by a vertex, and we have these edges, just doing an ordinary graph in which edges go between pairs of vertices doesn't really accurately describe these reactions, these multi-way reactions. So instead, we really need a hypergraph which has hyperedges. So here, this hyperedge E, it's a single edge now in a hypergraph, and rather than going between a pair of vertices, the edge has a tail, which is the set of vertices that the edge comes out of. These are the input reactants. And it has a head, which is the set of vertices that the edge goes into. This is a directed hyperedge. And that's the set of products from the reaction. So we're going to be working with hypergraph models where we have edges of this form, hyperedges. So just to make a little bit more concrete visually of what's going on here. So we have a source compound S on the left, we have a target molecule T on the right, and we have various reactions in the network represented by these vertices and hyperedges representing each reaction. These compounds and the reactions are annotated with stoichiometries. And now we're going to be looking at a factory which specifies a flux on each of the reactions. And this factory produces all the targets from the sources. So in green are labeled flux values on these various reactions. Notice that some of the reactions have flux value 0 on them. This really means that that particular reaction is not used by this particular factory. Now, in these green edges here, there's 2 different types of conditions we may impose on the reactions in the factory. One is that it satisfies conservation at all compounds. So here we have a red compound highlighted. And if we look at the total amount of material being used, consumed by the reaction, and the total amount being produced, that's equal. So it's this particular compound in red is neither accumulating or being depleted. It's staying constant. That's conservation. If we look at this other vertex here in red, on contrast in that vertex, more of that vertex is actually being produced by the reaction coming into it than is being consumed by the reaction coming out of it. And we call that accumulation. So really, if I have a factory under accumulation, all of the intermediate compounds, other than the source and the targets, will not be depleted as the reaction proceeds. And we generally call that accumulation. So we're either going to have conservation holding at all the compounds in the network or accumulation everywhere. Now, one of these issues that comes up and actually had not been studied that carefully in the prior work on this problem is that we can actually have degenerate solutions. So here is in green a flux shown that under the stoichiometries annotating these reactions is actually a legitimate factory. It's producing the target in a non-zero amount T, and yet it doesn't use any of the source compounds. This is a kind of solution that can arise when we're designing algorithms and computing solutions, which has been kind of overlooked in the past. And that's something that we're going to directly address in our work here. So that's actually a degenerate type of factory that can arise when you're solving a computational model. So we're going to look at the problem of computing a factory, finding this flux that ends up producing all the targets from the sources, and that is shortest. So here we're going to look at a problem in which these reactions are weighted. In the simplest case, we can have simply unit weights on every reactions, on all the reactions. And then if we compute a shortest factory, a factory such that the reactions that have non-zero flux on them, the sum of their weights is minimum, with unit weights, that's going to be finding a factory that uses the fewest reactions in order to produce all the targets from the sources. That's the problem we're going to mostly be focusing on in this presentation. And that problem is actually provably NP complete. So finding a shortest factory that uses the minimum number of reactions, or in general, minimizes weights on the reactions, for instance, in a likelihood model, that problem is NP complete or computationally intractable in the worst case. So we're not going to be able to design algorithms that actually achieve guaranteed fast running times, like polynomial running time, because this problem is intrinsically hard. So general, we're going to find these metabolic fluxes, which are non-negative real values on each reaction, specifying the relative usage of them. We're going to call an active hyperedge in a factory one which has non-zero flux on its reaction, so strictly positive flux. We have a stoichiometry matrix that summarizes the stoichiometries on all the reactions and all the metabolites. And we have these two conditions that the metabolic flux must satisfy on the intermediate metabolites. Those are compounds that are neither sources nor targets. And either we have to have conservation holding, as we stated, or we have to have accumulation holding. And both those constraints can be written as matrix vector products, in which we have the value 0 on all the involved compounds, or non-negative values for accumulation. So again, a factory specifies a flux, which produces all the targets from the sources and satisfies either accumulation at all intermediate metabolites or conservation at all intermediate metabolites. So in this talk, I'd like to contrast two different models, factories versus hyperpaths. So in a factory, one of the kind of interesting properties of it, shown by the factory on the left, is that the reactions can actually be using input reactants that are not yet produced by the reactions in the factory. So for that to happen, as the factory is consuming an intermediate metabolite, it must also be producing it as well under accumulation or conservation. And as well, we can have factories that I mentioned before that are degenerate. So factories that are producing the target without actually using any sources. And we've proved in our work that this can only happen when we actually have misannotations of stoichiometries in the underlying metabolic network. And our computational results say that that's actually not uncommon. There are many targets for which the only factory in our standard metabolic network databases that produces a target are actually only degenerate factories. So we'll point that out a little bit later in the talk when we look at computational experiments. So to summarize the difference between these two models, factories and hyperpaths, a factory, as shown the one below on the left, it can consume reactants before they're actually produced by the reactions yet in the factory. We have stoichiometries that must be satisfied everywhere, accumulation or conservation. And a factory can actually have these unfortunate degenerate solutions that arise and actually rise in practice. In contrast, hyperpaths are also collections of reactions that produce all the targets from the sources. But the one requirement and property of hyperpath is that reactants, so these reactions occur in an ordered cascade. There's a total order on reactions. And in that total order, for each reaction, its reactants, its input reactants, are always produced by prior reactions in the series before they are ever consumed by any reaction. So there's this ordering relationship in hyperpaths. One thing about hyperpaths is that they don't have to satisfy any stoichiometry constraints. There's simply a purely graph theoretic structure on reactions, so they can actually be computed when stoichiometries are not known for certain reactions in the network. And they also don't have any of these degenerate solutions that can arise with factories. So both these models, computing a shortest factory or a shortest hyperpath, hyperpath produces targets from sources just like factories. And for hyperpath, we're interested in also minimizing the total length. So minimizing a weighted sum over the reactions that it uses. Both those problems are both NP complete. So here's an example of an actually computed, provably optimal factory. So here in this, we are looking at instances where we have unit weights on all of the reactions in the metabolic network. So if we find a shortest factory, we're really finding a factory that uses the fewest number of reactions to produce the target. So here our target compound is at the lower right in the picture. And across the top of the figure are the sources that are actually used by this particular factory. And this is a provably optimal factory that uses the fewest number of reactions, has the minimum number of hyperedges in it in order to produce the target on the lower right. One thing to notice about it is that this reaction that's been identified in red here really distinguishes this factory from being a hyperpath, and then it's using the two compounds at the bottom, NADH and hydrogen above it, in order to produce the compound's intermediate metabolites without actually having produced those yet. So this is a factory that is definitely not a hyperpath. We can contrast it with a shortest hyperpath that's producing the same target. And for this particular metabolic network, this is an optimal hyperpath. It's using the minimum number of hyperedges, minimum number of reactions. Again, in this hyperpath, it must be the case that these edges can be ordered such that for each reaction, the input reactants are produced before the output products that it consumes. And we can see that that constraint actually requires us to use more reactions. So this shortest hyperpath differs from that shortest factory by these two reactions on the left. So it actually uses one more reaction than the optimum factory. And here we can contrast exactly how these two solutions differ. The single red reaction in the shortest factory has been replaced by two green reactions in the shortest hyperpath. And we observe experimentally that typically shortest factories often have fewer reactions than the shortest hyperpath. And later we'll actually give a theorem that explains why this is the case. So there's another model of finding optimal factories that's been in the literature. It was pioneered by Marie-France Segau's group. And this is who did the original work on computing factories. And this is a min-source factory model. So here, I'm trying to find a factory that produces all the targets from a set of candidate sources. And here we're interested in finding a factory that uses the fewest possible sources. And this is an example of a min-source factory, one that produces that same target as the prior solutions. But here we're actually minimizing the number of sources used, uses fewer sources in either that min-edge factory or that shortest hyperpath. And what we can see that tends to happen in practice is that when we compute min-source factories, we tend to use many more reactions in the optimal solution. In minimizing the number of source compounds used, we are often driven to use more reactions, actually. That's the case here. And in an optimal solution that minimizes the number of sources, we can also get these structures that are cycles arising in the solution, which have non-zero flux on them, but do not actually contribute to producing the target. So these are effectively useless cycles in the factory, but which arise computationally when you solve the min-source factory problem. So here's a comparison of the reactions used in a min-edge factory. That's the one that uses the single red edge. They all use the black edges, compared to the min-source factory, which uses many more green edges, but actually has two fewer sources that it uses than the min-edge factory. So one advantage of the min factory model is that when we compute solutions, we never get these useless cycles because they can always be trimmed which would produce a shorter factory. All right, so just a quick summary of related work on factories. This work was really pioneered by Marie-France Segau's group. They solved, for the first time, the min-source factory problem, which we just discussed. And they did this by solving a mixed integer linear program. And one thing that I want to point out here is that these methods for factories all have internal parameters to the algorithm that must be set. So here, this particular work on min-source factories had 3 different parameters that had to be set internally in the algorithm. We did the initial work in 2022 on this min-edge factory formulation. We're trying to minimize the number of reactions or a weighted sum of reactions. And even that, this is in this tool called Odin that we released. And even there, we have an internal parameter to the algorithm that has to be set. In contrast, on hyperpaths, as we said, that's a model where you don't have stoichiometries, but where these reactions are actually ordered. That problem's also NP-complete, and the really first work on solving that problem to optimality was done by Morali and Ritz. They designed an exact algorithm that computed a guaranteed shortest hyperpaths, but could only find hyperpaths that are acyclic, in which there are no cycles within the reactions. And that rules out many biological solutions of interest, because typically you do have cycles in solutions. And we developed the first a heuristic for the shortest hyperpath problem that's fully general, that allows hyperpaths that do contain cycles, which occurs in general. And this heuristic is guaranteed to run in polynomial time. It's guaranteed to be fast. But because the problem is NP-complete, it's only a heuristic. It's not guaranteed to compute an optimal solution, an actual shortest one. Computationally, in practice, it tends to compute solutions that are very close to optimal. And then we recently developed an exact algorithm for the fully general problem of computing shortest hyperpaths. Right. So one thing I want to point out is that all these prior methods for both factories have a target production parameter that's going to essentially guarantee that the solution produces the targets in some non-zero amount. There's a real shortcoming, because it's not clear how to set this parameter, internal parameter to the algorithm. If the target production parameter is too high, then you can get a solution which actually excludes factories that can only produce the target in a smaller amount than the desired amount epsilon. And those factories can be optimal. So an actual solution computed by the algorithm can be a suboptimal factory, because you've excluded these optimal solutions that don't meet the target production constraint for the particular parameter value. On the other hand, if the parameter epsilon is too low, we get numerical errors in the MLP solver. So you actually get solutions that are degenerate. So it's very unclear how to determine the right value of this parameter epsilon. So the contributions of our work: we developed the first robust algorithm for shortest factories. It's robust in the sense that it can never miss a valid factory, because it has no internal parameters that must be set. So there's no longer this issue of what's the right value parameter, and if I've picked the wrong value, am I actually computing a suboptimal solution? That can never occur, because our robust algorithm doesn't have any parameters. It's parameter free. And also, we address this issue of degeneracy in solutions, and we have an algorithm that compute the optimal solution that's guaranteed to be non-degenerate. In addition, we also characterize for the first time the structure of reactions in shortest factories. Prior to this work, it wasn't actually known, what exactly is the structure of these reactions that you get when you compute a shortest factory. We have a complete characterization of that. And we're finally able to unify these two models of hyperpaths and factories by proving that hyperpaths are actually a subclass of factories. Every hyperpath is actually a factory, but factories are actually more general. And our exact algorithm for computing robust optimal factories, it's fast in practice. We did a comprehensive evaluation over all the known metabolic network databases. and has a medium runtime of under 5 seconds on a laptop. So it's very fast in practice, even though it's computing a provably optimal, guaranteed non-degenerate solution. And this is implemented in our tool Freeia, which is freely available. Okay, so I see that I just have about 5 minutes, so I'm going to really quickly go through a description of the methods here. So the input is this hypergraph, whose edges correspond to reactions, whose vertices correspond to compounds, and a stoichiometry matrix, annotating these reactions with stoichiometries. We have a set of candidate sources, which the factory can use, might not use all of them, may only use a subset of them, so these are really just candidates for the sources. And then we have a set of target molecules disjoint from the sources, all of which must be produced by the factory that we're trying to find. The output is this flux on reactions. For intermediate metabolites, it either satisfies conservation everywhere or accumulation everywhere, really non-depletion everywhere. And every one of these targets in our target set has to be produced in some non-zero amount. Finally, we're finding a solution that minimizes the weights of the active hyperedges, the total weight of the reactions that are actually used by the factory. So there's prior work developed this parameter-based solution method by tackling a mixed integer linear program. The variables really correspond to the hyperedges. We have flux variables. We can always scale fluxes so in the range 0 to 1, and we do that in this formulation. And then we have, in addition, integer valued variables. These are the integer variables, and they're either 0 or 1, they're binary, and the variable is going to indicate whether or not that reaction is used by the factory. This is modeled by constraints. We have the integer variable x for an edge, has to be at least the flux value for that edge. So if we have non-zero flux, the integer variable is going to have value 1. And then we have the conservation accumulation constraints everywhere on fluxes. And then we have a target production constraint. We want to produce each target. For each target T in the set, we have that the total flux coming into that target has to be at least epsilon, where we have this non-zero parameter epsilon. The objective function is to minimize the total weight of the hyperedges. So our new parameter-free algorithm modifies this mixed integer linear programming by changing the target production constraint, which we actually removed, and changing the objective function. So we remove that target production constraint, and instead we put a constraint that says that the total weight of the edges used by the factory has to be at most some constant L. So this is an upper limit on the length, total length of the optimal factory. And we change our objective function to be, we're trying to find a solution, fluxes that maximize the production of all targets. Now, it looks like we've introduced another parameter here, L, the limit on the length, but we can actually eliminate L by doing a binary search or bisection over all possible values for it. So now our method is going to actually solve a series of MLPs where we actually find this optimal value of the length limit L, we find the shortest factory, while guaranteeing that we're producing all the targets. I want to mention that we have a characterization theorem. So we worked out that there are actually 3 classes of solutions to factories. Something's called trails, whirls, and eddies. Whirls correspond to equilibrium solutions that don't actually produce the targets in a non-zero amount. They just conserve their current amount. And eddies, which are these degenerate solutions that are producing targets without using any sources. And then we have trails. Trails are actually the non-degenerate solutions we want to find. So we finally have a characterization of what exactly these optimal solutions look like. There's only one class, trails, which are non-degenerate, and we have an algorithm that's guaranteed to find an optimal trail, an optimal non-degenerate solution. The other result we have is that it's actually the case that for any hyperpath that you have that produces the targets from the sources, there exists a flux on the edges in the hyperpath that actually make it a factory, that actually make it satisfy accumulation everywhere. So this really shows that hyperpaths are actually a subclass of factories. This result holds for any stoichiometries that are on the reactions. And it really implies that shortest factories can never be longer than shortest hyperpaths, and in fact may often be shorter, and this is borne out computationally. So for results, we looked at doing exhaustive computational experiments over all of Reactome and the 7 organismal databases in MetExplore. These hypergraphs are relatively large, up to 20,000 vertices, 12,000 hyperedges, 8,000 sources. These are compounds that don't have any incoming reactions, hyperedges, and targets. Those are compounds that don't have any outgoing reactions. So looking at Reactome, for instance, it has 5,000 target instances. We computed optimal factories for every one of those targets, and there's 4,000 of those targets that actually have factories under accumulation, 1,600 that have factories under conservation. So it's much harder to find a factory under conservation, much more severe constraint. And there's 2,400 that actually have hyperpaths. So I want to emphasize that this new parameter-free algorithm, Freeia, it's outperforming the prior state-of-the-art. The prior state-of-the-art Odin failed when the parameter value was not chosen well. Our new tool Freeia can actually determine the best possible value that exists for that parameter. And in doing so, we can actually show that there's no single parameter value for the parameter-based methods that works for every possible target. We can show that every possible value that you could choose for the parameter fails for some target from Reactome, for instance. I'll just quickly go through the rest. Here's an example of a solution. This is a factory producing cholesterol as a target that could not be found by prior work because there's no valid value for the target production parameter under which an optimal solution corresponds to this particular one, which we can find by Freeia, which is a parameter-free method. So just to conclude, we've given the first robust algorithm for finding optimal factories. It's parameter-free and degeneracy-free. We gave a characterization of the structure of optimal factories. We unified these 2 pathway models. We can do this very quickly in practice, and all the implementation data sets are available at our site, freeia.cs.arizona. And there's many future ways in which we can continue this line of research. Our parameter-free algorithm is actually only for the special case of positive edge weights. It'd be interesting to see if there's a algorithm that's parameter-free for the general case of edge weights that can be positive or negative. And our characterization is really only for general edge weights. We don't really know a characterization of the structure when edge weights are constrained to be strictly positive. It'd be nice to see if we can have a fast heuristic for shortest factories. Our exact algorithm, in the worst case, can take exponential time. And it'd be, I think, relatively important to really study, can you find solutions that don't have interference from negative regulators within the reactions used by the factory? So I'll just conclude there. Here's our citation, Journal of Computational Biology, and here's a picture of Spencer and myself. Thank you.